All right, now we're going to get into the nuts and bolts of tensor calculus. In the last lecture, we proved that the Jacobians that correspond to the inverse coordinate transformations are the inverses of each other. And we actually proved it for the two-dimensional case. So our goal, it's not an important goal, but just to have a goal for this discussion, would be to prove the same Jacobian property, but for arbitrary dimensions. And we'll use that as an excuse to introduce in DCL notation, I usually call it the tensor notation, because it's extremely effective at these sorts of calculations and all the other calculations in the textbook. So this week will actually be very hard work, and maybe next week will be a lot of hard work. And then from then on, everything just rolls with complete ease. So this is where, tensor calculus makes a lot of difficult computations very simple, but you have to put in the legwork. So the legwork happens now. So we'll consider the example that's considered in the book, which is we have a function of three variables, A, B, and C, but we'll give them numbers of A1. We'll write the index on top. The importance of all of this will become clear very, very soon. And each one of these is a function of mu and theta, or mu and nu. So A1 is a function of mu and nu. A2 is a function of mu and nu. Well, actually, in the book I start differently. I call them X, Y, and Z.
A, B.
A, B, and C? Let's do that. All right. I think it's worth it. A, B, and C. And each one of these is a function of mu and nu. So be on your toes, because right here, A represents two different things. When it's here, it's an independent variable. But when it's here, it represents a function of mu and nu. So this overloading of letters happens all the time. So just be aware of what A, B, and C we mean. So if these expressions are plugged into these expressions, into this expression, we get a new function, little f, and this one is a function of mu and nu. And it's formed by putting together this combined function, A of mu and nu, B of mu and nu, and C of mu and nu. A lot of writing, but that's kind of the point. And DCL notation will save us all of this writing. And we're now going to evaluate the partial derivative of f with respect to mu. And we'll of course use the chain rule on the right hand side. And it's when you use the chain rule is where the DCL notation really invites itself and is perfect for expressing. So df d mu is of course d capital F dA d mu plus df dB d mu plus dfdc dc du. My arm is getting tired because I didn't use the tensor notation. Okay, so this is the chain rule. So step number one towards converting this to tensor notation is to rename these variables instead of A, B, and C, to rename them A1, A2, A3. And now f can be written as a function of A1, A2, or A3. That's one way to denote it. Another way to denote it is to just say f is a function of the collection of a's. Here, this would be my least favorite way to denote it, which is to just say ai. And we'll reserve a much more significant function to the indices, so we will not use this notation. So what we will actually do is suppress indices altogether, and we'll just write f of a. F of a. And what you need to remember is that whenever you see something like this throughout this course, we actually mean something like this. It's just that you completely suppress the indices. Makes the notation short. So now the combined function, let me erase this. Now the combined function f of mu can be written as f of a of mu and mu. So already a little bit more compact. Now let's write the chain rule. So I will once again write it the long way, and then we'll use Einstein's notation to compress it greatly. We have df d mu equals df dA1 d mu plus df dA2 d mu plus df dA3 d mu. And of course, what's nice about indexing the arguments of f is that you can now use the summation formula. It's the summation of I from 1 to 3 of df dAi d mu. So much more compact, and I'm actually glad that this is taking a long time, because it takes a long time to get used to it. So you might as well take a long time writing this out, because that's when the idea of what these compact expressions represent sort of sink into you. We'll be dealing with a lot of expressions like this, so get used to what they mean. Early on, whenever I see something like this, I unwrap them in my mind and try to visualize what they represent. What they represent is usually a sum of individual terms. Okay, so let me write down the summary here. So this doesn't use Einstein's convention yet, but Einstein's convention is this. When the same index appears on the top and the bottom, the summation is implied, and you don't need to write it. It seems like a small deal, but it's a huge deal. It's in terms of how your brain works psychologically, it makes all the difference in the world. And with it, it carries quite a few implications of what you can do with the expressions that you encounter, and all of those implications are correct, which is very important. It's the kind of notation that invites you to do the right thing. And when I said on the bottom, so this index is clearly on top, but this index is on top here, on top of this letter, but the whole thing is on the bottom, so I count it as a bottom index. I'm trying to make sense of it all, I would call this an upper index, and this being on the top of the bottom is a bottom index. So Einstein notation kicks in. An upper index and a lower index, therefore summation is implied. We can therefore write df d mu equals df dai d mu. You guys have any questions? Nice and compact. And now I won't be too lazy to write what df d mu is. df d mu. df d mu is df dai dai d mu. It's almost as if the tensor notation was invented for writing out chain rules, applications of chain rules, because these are the terms that arise. Quite nice. So it's a pair of expressions. So of course the tensor notation goes a step further and combines them by calling these variables mu1 and mu2. Index these variables as well. So now you can write f of mu1, mu2 equals f of a of mu1, mu2. And remember that when you see this, it means a1 of mu1, mu2, a2 of mu1, mu2, and a3 of mu1, mu2, but compressed into this notation. Similarly, I won't even write it down. You can write that f of mu I equals capital F of a of mu I. That's my least favorite. And the one that we'll use, of course, is that f of mu, remembering that this notation means f of mu1 comma mu2 equals f of a of mu. So things are becoming very much compressed, because the way this reads is, I'll do it once, f of a1 of mu1, mu2, comma, a2 of mu1, mu2, comma, a3 of mu1, mu2. All of that is compressed into this simple notation. Yes?
Just given that last statement, how do you know how many A's and how many mu's?
You have to know from the setup of the problem.
Okay.
The problem will dictate. If you're in 3 dimensions, it's 3. If you're in a surface, it's 2. If it's the interplay of surfaces and ambient spaces, then one is 3, the other one is 2. Exactly right. And because in our example, mu and nu is 2 variables, so we only have mu1 and mu2. Collectively, we'll denote them by mu alpha. So whenever we use Greek indices, it means that we have values 1 and 2. And whenever we use Latin indices, that means values 1, 2, and 3. So let's now combine. Let's write them out first with this new notation. We now have df d mu alpha. Nope, that's not what I promised. Mu1 equals df d ai d ai d mu 1 and df d mu 2 equals df dai dai d mu 2. So pair of identities, which we'll now enumerate with the help of an index. We'll call this mu alpha combined. So combined, it looks like this. Kind of beautiful in how compactly we can represent such involved expressions. df d mu alpha equals d capital F d a I d a I d mu alpha. And this deserves to be boxed. So a little bit of terminology having to do with this expression. So this identity represents two different identities. One when alpha is 1, and one when alpha is 2. So alpha, you can ask, what is this saying when alpha equals 1? And the answer be, that's what it's saying when alpha equals 1. And you can also ask the question, what is this saying when alpha equals 2? And the answer is, this is what it's saying when alpha equals 2. Now here comes a nonsensical question. What is this saying when I is 1? And that's not even a valid question, because I here represents summation. I runs through the values 1, 2, and 3. So the right-hand side has 3 terms in it, and that's what the function of I is. So here, the index I and the index alpha have different functions. Alpha, here comes the synonym, it's called the live index, or the free index. I think there's another synonym. So it represents that this identity actually stands for several different identities, one for each value of alpha. This I represents summation, and it's called a dummy index, or a silent index, or a contracted index. Dummy, silent, contracted. That's pretty much it. And it can be renamed to anything. So for example, I could say dfi daj, daj d mu alpha. It can be switched to any letter because it represents the summation. Any other letter can represent the summation. So you're free to rename them. With alpha, you can't do that. You can't just arbitrarily rename this alpha into beta. You have to make it consistent on both sides. So if I wrote df d mu beta and repeated everything here d mu beta, that's perfectly valid. So a live index can also be renamed, but it has to be done so consistently on both sides. So actually, this is sufficient to prove the Jacobian property for any order. So it will actually be short, but extremely intense. Let's remind ourselves one last time, write down expressions without the tensor notation. And we'll use x and y and r and theta, even though this doesn't need to be specific to polar coordinates interacting with Cartesian coordinates. It can be for any two coordinate systems. But I'll just start writing where we finished the last lecture. So here's what we said. If we have a second coordinate system, which is given to us in terms of the original coordinate system, and in this function we plug in how x depends on r and theta, and how y depends on r and theta, and the result will be r, where this r, and this r are the independent variables, and this letter r denotes square root of x squared plus y squared if these are polar coordinates. It's a function on how the first new variable depends on the old variables. And the same thing for theta. Theta of x, of r, and theta, and of y, and r, and theta, equals, now we'll switch to this equals theta, because it's identically equals. And because these two functions, these two identities, are in fact identities in terms of r and theta, they can be differentiated with respect to r and theta. Let's see how far we want to go with this. Let's differentiate the first one with respect to r. We'll get dr dx, dx dr, plus dr dy dr, plus dy dr, I'm sorry, plus dr dy, plus dr dy dy dr equals, you tell me? 1. I think I'll just write one more. And dr, and now we're going to do the same thing with respect to theta. So dr dx, and it's very important once again to keep straight what each r represents and what each x represents. Dx d theta plus dr dy dy d theta equal 0. And we can get two more, so I'll put a big curly. So the big curly bracket represents that there are two more coming from this identity. So we have 4 identities in total, and we can arrange them into 2 by 2 tables, which exactly represent matrices, which exactly represents the fact that the Jacobian of the forward transformation times the Jacobian of the reverse transformation equals the identity matrix. And this can probably be generalized to, not probably, very easily generalized to 3 dimensions with a lot of writing. And then maybe with to n dimensions with a lot of writing where you would write dot, dot, dot. The tensor notation allows you to do all of this very easily. And not only very easily, but it's very necessary to do this to do many of the under the hood workings of tensor calculus. So let's see. Here is, we have to introduce a little bit of notation. We have 2 sets of variables. Zi, I'm going to call them the old variables. These are x and y. So z1 is x, z2 is y, z3 is z, if you want. These are the old variables. The new variables are denoted by zi prime. So, great invention. No, don't know who thought of it. To put the prime not on the letter, but on the index itself. It's almost like we have 1 prime, 2 prime, and 3 prime. But z1 prime is r, z2 prime is theta, z3 prime is perhaps 5 in spherical coordinates. And you can express one of them in terms of the other. So here we're expressing new in terms of old. So let's do the same thing here. So here, I'm going to write it in 2 different ways. What we're saying is that zi prime is a function denoted by the same letter, just like we did here. R was both the independent variable, but also the function that gives us new coordinates in terms of old coordinates. A function of the old coordinates. z1, z2, z3. So this is equivalent of saying that r equals square root of x squared plus y squared. That's for I prime equals 1. And when I equals 2, we would have theta equals arctan of y over x. This is giving us new coordinates in terms of old coordinates. And of course, we're going to once again suppress the indices of function variables, and we'll write this intense looking expression. Zi prime equals Zi prime of z. Because we've once again suppressed the indices of function arguments. You're good with this? Now, of course, there's a reverse relationship. And the reverse relationship in compressed form reads like this. Zi equals is a function of the prime variables. Here the prime goes on the letter itself because the index is suppressed. This is saying x equals r cosine theta, and y equals r sine theta, but in compressed form. I will erase this one because we need the space. Yes?
Isn't each one of those variables z1, z2, z3 a function of the prime variables?
I'm sorry?
So the z,
Tell me where to point. Here?
yeah, that one.
Yes.
Isn't that also a function of the
So
prime?
we're about to do this. So what this is saying right now is r equals square root of x squared plus y squared, which is what this is kind of saying. That's what r is a function of x and y. What we do next is what I'm about to do.
Okay.
Into that function, plug in how x depends on r and theta and how y depends on r and theta. And then you will recover z1. And if you do the same thing into the second one, then you will recover z2. Yes?
Couldn't you suppress the index on VI?
This one?
Yes.
Well, no, because I want this to be three identities. Just like this is here, two identities. I want it to be multiple identities. So this tells me right here, I keep going between saying 3 and 2, but now let's think that we're in space, so actually 3. So I want to make sure that I have three identities. One for r, one for theta, one for phi. That's here. And here I want to have three identities. One for x, in terms of r, theta, and phi. One for y, in terms of r, theta, and phi. And one for z, in terms of r, theta, and phi. So this, having a live index here, reminds me that this is actually three identities. Just like these are two identities. Well, let me write the equivalent of this. What this is saying, so I think this is the hardest part of the course. If you master this, everything else is a breeze. This and the next step. They're two toughest things in the course. This is the hard work. Everything else is easy and enjoyable. But actually, mastering this would help you with much more than tensor calculus, because you differentiate things all the time. And this actually teaches you how to differentiate things in the abstract. Okay, so the equivalent of this is saying that if I take my r, theta, and phi's, and I look at how they depend on the x, y's, and z's, and I then plug in how x, y's, and z's depend on the r, theta, and phi's, which just puts a prime here, then what I will recover is individually my r, thetas, and r's, thetas, and phi's, which is zi prime. This I is from before. There you go. You've got to understand what this means. This is the short for this, except with 3 or 4 or 5 or n variables. And we're about to take the derivative. And when you take the derivative, the chain rule happens. So, and the chain rule happens with two different indexes. One devoted to the summation, and one devoted to the free variable with respect to which you're taking the derivative. So the one index will be responsible for summation, and one will represent z1 prime, z2 prime, and z3 prime. So this is three identities. Each one of them will be differentiated with respect to three different variables, but all at once. Just like when we wrote df d mu alpha, it was capturing the derivatives with respect to d mu 1 and d mu 2, but at once. And we're going to take the derivative here with respect to the free variables. These are the independent variables. And these guys represent the functions that are right here. This is r and theta in terms of r and theta in terms of x and y. And this is x and y. Let's go to 3 dimensions. This is r theta and phi in terms of x, y, and z. And this is x, y, and z in terms of r theta and phi. So if I were to actually write out what this means, it would have 9 terms in it. Because it's, and then 3 times over. because this is z1, z2, z3, and each one is a function of z1 prime, z2 prime, and z3 prime. So it would be completely impractical to write it. Okay, let's focus for the moment on the right-hand side. On the right-hand side, which in the first one represents R. What does I mean by the first one? When I prime equals 1 prime, I should say 1 prime. So when I equals 1, this says something like this. R with all of this stuff plugged in gives you R, because that's what Z1 prime is. When I equals 2, it's an equivalent of this expression. Theta, as a function of x, y, and z, plug in how x, y, and z depend on r, theta, and phi, will recover theta. And finally, phi, when I equals 3, as a function of x, y, and z, when you once again plug in r, theta, and phi, will recover phi, because that's what this represents when I is 3. Make sense? Now let's take a derivative of it with respect to all three at once, just like we did here. So we will take the derivative of both sides with respect to d, so I'll write it on the side. Here's what we'll be taking the derivative with respect to. We want to take the derivative with respect to each one of the independent variables. So it has to be a derivative. It cannot be a derivative with respect to dzi prime. Because if you wrote something like that, you can look at it and say, hey, the right-hand side depends on zi prime, which means z1, z2, z3. So let's take the derivative with respect to zi prime. But that would be a problem because that would invoke the Einstein notation, the convention, and represent some kind of summation, which we don't want to do. What we want to do is how these two led to 4. Those 3 will lead to 9, so we want to capture all 9. So what you actually need to do, this might require an additional discussion. In retrospect, you'll get used to this and you'll think that it's the most natural thing. But you have to do J prime. You have to use a different letter so that you get all 9 possible derivatives. dr, 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 d theta, dr, d phi, d theta, dr, d theta, d theta, d theta, d phi, and finally d phi, dr, d phi, d theta, d phi, d phi. So each one of these 3 needs to be differentiated with respect to each one of the 3 independent variables. Let's think about first what happens on the right-hand side. So let's consider, actually I will erase this. But this is a very good discussion. What is dzi prime? dzj prime as independent variables. So, question number 1, when I write equals, and whatever the answer is here, the first question is, how many relationship will our, let's just call it something like this, it will be answer I prime, j prime, that's what it'll look like. How many relationships does this represent?
N squared.
That's exactly right, 9. So n squared and 9 are equivalent for the purposes of this class. So if you mean n squared, you can just say 9. This represents 9 expressions. Let's write out a few of them. Just like here, one of them was dr. What was dr? R is the independent variable. dr. What was this? 1, right? So to understand what I'm asking for here, you should think back to this expression. And what we did here was this was an identity in R. So both sides can be differentiated with respect to R. This R is the independent variable R. So when we took the derivative of this identity with respect to R, you all said without a problem, 1. That's what that question is asking. It's dr, but captured all 3 at once. So what is dr? 1. Now let's look at I equals 1, j equals 2. That would be dr d theta. dr d theta, and this equals 0. Okay, that's great. I could write out 9 more, but you can kind of see what's happening. So can you describe in words what the answers are, what answer is in terms of I prime and J prime?
Kronecker delta.
Well, that's going 1.5 steps ahead.
Identity.
That's using matrix notation, which will soon be banned. But you can say it's 1 when I prime equals J prime, and 0 if I prime is not J prime. Is that a good description with words?
Yeah.
Yes, it is. And that's called the Kronecker delta. And it's denoted by delta. And of course, we have I prime on top, J prime on the bottom. To match what we have on the left-hand side. I prime on top, J prime on the bottom. And that's the only way the delta will appear. You can forget about delta with both of them on the bottom. Yes.
The position of the I and J does it really
Which
matter?
one's first, which one's second? That's an unbelievable question. I can't believe it came this early. It technically does. So it would be much cleaner to write it like this. But then you'll see there will be one. So I is first, J is second. But we write I, but you can kind of ignore this and write them more sloppily like this, because you can kind of adopt the convention, say this one, the top one is first, the bottom one is second. Just remember that. But even that, with respect to this special symbol, becomes unimportant. But there are situations where you really need to worry about it. So, now we're kind of ready to differentiate this identity. And you can never turn off your brain when you do that. There's lots of things that the notation takes care of for you, and you don't have to think about it. What you always have to think about is what are the independent variables in the identity and what are the functions. Without that, you would be completely lost. Because this zi prime is a function. And this zi prime is the independent variable. So that has to be clear at every step. Everything else, the tensor notation will take care of for you. All right. Let's apply the chain rule. We're going to take the derivatives of both sides with respect to J prime. So on the right-hand side, we'll have delta I prime J prime. And it's a beautiful way of at once capturing these 9 zeros and ones. Great. On the left-hand side, we have to use the chain rule. And when we used the chain rule, when we did this, remember we said D capital F, DAI, D mu alpha? I appeared. There was a new index that just appeared from just applying the chain rule. So the new index will have to appear here. Because when I apply the chain rule, let's take half a step back to this expression and remind ourselves of how we applied the chain rule. It was dr dx, dx dr plus dr dy, dy dr. That's where this came from. So here it's going to be dzi prime, first this will be x and y, right? It'll be dx, and then dx dzj prime. So it actually looks like this. Here's the chain rule in one step, but I'm going to line it up with the equal sign. D, Z, I will rewrite this later. I think it needs to have its own space. D, Z, I prime. D, Z, now I can use I, just like I would have used I here. Different from I prime. This is, let me write it out. D, Z, I, D, Z, J prime equals delta I prime, J prime. And we're going to talk about this for a while, because this is kind of incredible. This is kind of incredible It's kind of incredible because it's capturing what would have been these nine identities. Each one a mess. Each one with 3 terms. Each of the terms with 2 products. Would have been a complete mess to write out all 9. It captures them all in this compact expression. So to understand what a tensor expression is saying early on, you kind of have to do this. You have to, first of all, explain to yourself, how many identities am I looking at? And the answer here is 9, because I prime is a free index, see, matching up with this I prime, and J prime is a free index, matching up with this J prime. So there are 9 identities. Each identity on the left-hand side includes 3 terms, because there's contraction on I. Is it running?
Yeah, that's it.
Okay, good. I'm almost done with this segment. There's a contraction on I. So 3 terms. So if you were to write it all out, there would be 27 terms. And you won't be able to do much with them because it would be a mess. But here it's extremely compact. So if you really want to explain to yourself, what is it saying? Take particular values. So let's take I prime equals 1. Oops. I prime equals 1. And let's take J prime equals 2. Equals 2. So this is 0. Delta 1, 2 equals 0. I shouldn't have crossed it out. And what now? And Z1 is R. And this should have been 1 prime, and this should really be 2 prime, as it's the quote-unquote new coordinate system. And this is theta. And I can remember that these represent x, y, and z. So what the first of the 9, not the first, what one of the 9 identities is saying is that dr dx, dx d theta, plus dr dy, dy d theta, plus dr d phi d theta equals 0. We almost have it right here, right? dr dx, dx d theta, plus dr dy, dy d theta. In 3 dimensions, it would have been dr dz, dz d theta. Was I saying phi? I said something wrong. Let me do it again. What this is saying is dr dx, dx d theta. Oh, that's what I was saying wrong. Okay. dr dx, dx d theta, plus dr dy, dy d theta, plus dr dz, dz d theta equals 0. And that's basically what this is saying. dr dx, dx d theta, plus dr dy, dy d theta, plus dr dz, dz d theta equals 0. So this is just a, can I say brilliant way of encoding the 27 terms among 3 identities in one simple compact expression. All right, let's complete the segment. Pause it. All right, let's spend a few minutes talking about the matrix product in the tensor notation. How would we represent AB equals C in matrix notation? Let's remind ourselves. A might be matrix like this. This is all we're on our way towards banning the word matrix. Matrices are perfect for some things, and actually for some things with regard to tensor calculus, when we say that the contravariant metric tensor is the matrix inverse of the covariant metric tensor, matrices play an important role, but most of the time they will be misleading except for the most basic identities. So here's the matrix A, here's the matrix B, here's the matrix C. How do we obtain, let's say, 3rd row, 2nd column, this entry right here? Let's give it a name. This is C, this entry right here is C32. C32. For that we need to quote-unquote dot the 3rd row of this with the 2nd column of this. So I see a summation happening. C32 is this times this, plus this times this, plus this times this. I don't know how, 5 by 5, plus this times this. That's what C32 is. So let's capture the elements here with indices. I claim that this is A, 3I. Is that right? They're all in the third row, A3I. And these all are B, I, 2. So, A3I times BI2 equals C32. Of course, the Einstein convention does not kick in because both of these i's are on the bottom. So I have to put a summation sign over I think from 1 to 5. But the important feature here is that the second index is it's the second index of A that matches up the first index of B. That's telling you that we're traveling along the row of A and along the column of B. And of course this is true for any entry. So now we'll write it in fully indicial notation. Instead of this, I will now write, which is the same thing, but entry by entry. Well, I actually want Cij in the end. So it'll be Aik Bkj equals Cij with a summation sign over K. See, these dummy indices get renamed mercilessly. I can give them whatever name I want. It doesn't change any meaning. Okay. So the important thing to see is that it's the second index of A and the first index of B. One step towards the matrix notation. Perhaps I erased it too soon. Instead of calling my entries here A, I, J, I will instead call them A, I, J, with the understanding that the upper index is first and the lower index is second. You see, the order of indices matters greatly. If I wrote this as AKI, if you think about it, I'm effectively taking the transpose of A, because I'm traveling down the column of A instead of traveling down the row of A. If this said Ki, and K is the one that's changing, that means I'm traveling down the column of A. So in effect, from the matrix notation point of view, I'm multiplying A transpose and not A. So the order of indices is very important. So upper is first, lower is second. It's nice even matrix notation comes with upper and lower indices. Something, the discussion we had off camera. All the best things in life come in pairs, where one is naturally represented by an upper index and the other is naturally represented by a lower index. The same thing for B, the same thing for C. I'm just changing, I see a few skeptical glances. Don't be skeptical about this, I'm just changing the placement of the index. Not very objectionable. So then it becomes A, I, K, remember I is first, K is second, times B, K, J equals C, I, J. And this has, and I no longer need the summation sign because now I have Einstein's convention working. Because K appears one as a lower index, one as an upper index. And it means exactly what it did before. It means exactly what we did before. Just a different way of writing the matrix product. And this has a few terrific advantages over the matrix notation, and a few terrific disadvantages for lots of linear algebra type things. So for linear algebra type things, this is atrocious. For multivariable calculus, this is great. So we'll use the right notation for the right problem. But let me let me have you take it in. So a matrix product is n squared identities, right? Because you have to indicate how each entry of the answer is obtained from the entries of the inputs. So it's n squared, 9 and 9 identities. And each one is a dot product of a row versus and a column. So that product includes 3 terms. And that's what this dummy index represents.
Would it be ij more generously if we're in matrix, or are we not?
Say it again?
Like if you had k of 2 by, if they weren't both square.
Oh, if there were, yeah, this works just as well. Yeah, in tensor calculus, we will have things that are not square. This works perfectly. Let me tell you about the advantages of this notation. The first one will be a total surprise. A total surprise, I think. And you have to get used to it. The order of the terms doesn't matter. This is kind of an advantage of this notation. Check this out. I can easily write this. I'm not messing with indices. The indices come with the letter. A, I, K equals C, I, J. This is completely equivalent because AIK is not the matrix itself, it's the entry in the matrix. This is writing the matrix product explicitly in terms of the entries of the matrix. So in this summation, right, this is just an entry, this is just an entry. If I switch them around, well, I'm just switching 2 numbers. A1, 2 could be 3, and B2, 3 could be 7, so then it reads 3 times 7. If I wrote these 2 symbols in the opposite order, then it would be 7 times 3, the exact same things. Remember, in the DCL notation, in the tensor notation, you are referring directly to the entries of the object. So this notation is exactly equivalent to this. They're just individual numbers. They always are. Nothing but individual numbers. They could be r, theta, and phi, individual numbers, x, y, and z, and this times the entries of the matrix, they're individual numbers. Because now if I ask, what's C, what would we do, 2, 3? I would look here and I would say, well, it's C, 2, 3. What is C, 2, 3? So this needs to be 2, this needs to be 3. It's B1, 3, A, 2, 1, plus B2, 3, A2, 2, plus A, plus B, 3, 3, A2, 3. The exact same thing as I would have said here. A2, 1, B1, 2, 1, 3, A2, 2, B2, 3, A2, 3, B3, 3. Add it. Say the exact same terms, the exact same entries. That's very nice. So you don't have to worry about the order of the terms, even though if you wrote it in the matrix notation, the order would matter. I can also multiply by A transpose. I would just have to switch the order of the indices. I would have to say the first index on A, right? I would then need to write A where the first index is lower. So at this point you can look at it as just putting indices where you find them convenient. But if I wrote it this way, the first index of A is contracted, summed over with the first index of B. This would represent A transpose B equals C. This is hard because you sort of have to rethink what you've known before. But there's an entire chapter devoted to linear algebra in tensor calculus terms, and it's discussed there. Yes?
Now, you switch the I and the K by moving their vertical position relative to one another. Can you switch them, like put the K on top of the A and the I on the bottom?
So right now this discussion is a little bit out of context of where this would have come from. So now let's introduce the Jacobian functions, the Jacobians. So remember the Jacobians, they are the Jacobians was this thing. dr dx, dr dy, d theta dx, d theta dy. So they're basically each of the new variables differentiated with respect to each of the old variables. Each of the new variables differentiated with respect to each of the old variables. So they're in effect, if here is how new variables depend on the old variables. This is r as a function of x and y. This is r as a function of x, y, and z. And theta, when I equals 2, as a function of x, y, and z. And theta, phi, as a function of x, y, and z. I have to differentiate each one of these with respect to x, and that will give me the first line, with respect to y, and that will give me the second line, and with respect to z, and that will give me column. I have to each one of these, I have to differentiate with respect to x, and that will give me the first column, with respect to y, and that will give me the next column, and with respect to z, and that will give me the third column. So it will affect, so the Jacobian that I have over here is really represented by this. It's dz I prime. dz I. That's the representation of this matrix, where this index is first, and this index is second. Let's assume this is 1, which is r. So then it reads dr dx, dr dy, right? When you change the second index, you're moving along the row. dr dz, this would have been over here. So this object is the Jacobian, and it's denoted by j I prime I equals j I prime I. So it's this kind of object in indicial notation, where I prime is the first index, I is the second. Yes?
I thought it had to be J in the bottom. It capture all derivatives.
Yeah, but I can use any letter. Sure. J. But I is free, so I used it. I'm going to go back to I.
Oh,
Sure.
Yeah.
I
It's
is different than I prime.
I is different than I prime.
Yeah, I prime is the truth.
Yeah. So the prime is introduced so we don't run out of letters in the alphabet. So some books go IJK for the primary coordinate system and RST for the new coordinate system. And then you run out of the alphabet, and sometimes they cross and you're not quite sure. P, for example, is that part of the IJK or is it RST? So it's I prime is actually a pretty good invention. So, but I prime is different from I. We could have used a different letter, but it's a good device for A, saving letters, and B, distinguishing new coordinates from old. So you guys buy that this is the Jacobian? Okay, great. Let's talk about the inverse relationship. So the inverse relationships would have read like this. Zi, which is x, y, and z, are functions of r, theta, and phi. So the first of these would be x as a function of r, theta, and phi. So r sine theta, cosine phi. The second one will be y as a function of r, theta, and phi. So r sine theta, sine phi. And finally, the last one will say that z is r cosine theta. That's if you want Cartesian and polar coordinates. So these can be differentiated in their own right, giving us this other Jacobian, which we claim as the matrix inverse of this one, which is dx, dr, dx, d theta, and dy, dr, dy, d theta. Let's capture it in indicial notation. It will be dzi, dz, j, well, I prime. And that's denoted by J. I can't believe I erased the other one. All right. It's going to come back here. So J I prime I is the first one. It's D Z I prime in terms of D Z I, where these are functions and these are the independent variables. And this one goes the other way. It's D I prime, where these are the functions and these are the independent variables. Let me give you an example of how I always talk to myself, because you'll have to talk to yourself this way as well. So when you look at these guys, when R is expressed as a function of x and y, and you evaluate these partial derivatives, they appear, the functions that appear here are also functions of x and y. You'll remember it from last lecture. We've got, what was this? X divided by square root of x squared plus y squared. This was y divided by square root of x squared plus y squared. So they naturally appeared. They were originally functions of x and y. You take partial derivatives, you once again get functions of x and y. These guys are opposite. X was a function of r and theta. Y was a function of r and theta, so these partials are functions of r and theta. This was r cosine theta, this was sine theta, this was minus r sine theta, and this was r cosine theta. So these are naturally functions of r and theta. So when I get back to these expressions, I always tell myself, these are naturally functions of old coordinates. So I'm calling the unprimed coordinates the old coordinates, and the prime coordinates the new coordinates. So when you evaluate this Jacobian by this partial differentiation, you will have a function of x and y's, because you're here. And when you evaluate this Jacobian, you will have a function of r and theta. So if you want to combine them, work with them at the same time in some way, you have to bring them to the same variables. They all, x's and y's, and r and thetas, all represent some points in space, and through that you have a connection. So at any point you can translate x and y into r and theta, and r and theta into x and y, and very often you have to do that. So let's see what this expression is telling us. This is the ta-da moment. This is this is J I prime I. Yes? J I prime I. This is J prime times J prime. Once again, remember, this is first index, second index, first index, second index, in actual word. Equals delta I prime I delta I. What am I saying? I was thinking about the next object. I just meant to copy this. All right. Thank God for the delete function in iMovie. And you see what this is saying? This is one of the last times you're allowed to say the word matrix. This Jacobian and this Jacobian multiply. This is the matrix multiplication. That's why we went over that. This just means that this multiplied by this as a matrix is, you're allowed to say it now, identity. So they are matrix inverses of each other. So, hold on. So this is proof. It's not really proof. It's the same thing we did before. Just tensor notation allows us to keep it compact. Without tensor notation, you wouldn't even see this so simply. And you could never take it to second order. We're about to take it to second order derivatives. So hold on to your seats. So with tensor notation, you can easily take it to second order or any other order you want, or you need. You only need one more order. That's all I have to say. Question?
If there was if that was an I prime instead of J prime in the lower index, would that
No,
imply
because
that-
this I prime would have this I prime would have kicked in Einstein's notation with this I prime.
Right, okay.
You could do it. I'm going to ask you your first tensor question. Are you ready for your first tensor question? What is delta I?
3.
Hey, isn't that nice? 3 is right. Or n. Do you understand why? Because when you have a repeated top index and a repeated bottom index, it activates Einstein summation convention. So this went straight to being a summation. And it's the summation of delta 1, 1 plus delta 2, 2 plus delta 3, 3. And what's delta 1, 1? 1 plus 1 plus 1, 3. Let me ask you a linear algebra terminology question. What is A, I? What is this called? Well, no, it's a number.
Oh.
Hold on, it's a number. So whenever I look at it at a tensor note as a tensor expression, the first question I ask myself, is it a number? Is it a system that's n by n? How many entries does it have? And I look at this is a number. So it's A11 plus A22 plus A33, which is known as
The trace.
the trace. So if I put I prime here, what I'm asked to do is evaluate this quote-unquote matrix and then find its trace. So here's kind of also a matrix question. A, I, J, B, J, I. How would you describe this in linear algebra terms?
Trace of the product.
Yes, this is the trace of AB. Because if this was K, then it would be just the product of A and B. You would say it's AB. But now you're asked to then take this product and evaluate its trace. So this is the trace of AB. It's also the trace of BA. If you first rename this into K, then you're actually looking at BA. That's right. Second index of B contracted with first index of A. That's BA. And then you're asked to do this, and it's the trace. So the trace of AB equals the trace of BA. So let me bring up one more important point. I alluded to it earlier when I said that Einstein's convention leads to your doing only the right things. So when you encounter an expression like this where there are two summations, y on I, y on j. By the way, this is the sum of how many terms here?
With the J,
Yeah, with I and j.
9.
9, right? A12, B21, A11, B11, A13, B31. All possible combinations are represented in the sum, 9. So the question might be, do I do a simultaneous sum? Or can I first do the sum on j followed by the sum on I? Or can I first do the sum on I followed by the sum of j? Which one's right? Well, all three evaluate to the same thing. It's very easy to show. It's one of the exercises. Any interpretation works equally well. Ready for next? Yes,
So the Jacobian has indices that are on the top and the bottom.
that's right.
And you said only bottom is covariant.
No. The Jacobians will not be described in terms of covariant and contravariant properties.
So there's no meaning to
No meaning to upper and lower, except it's nice that it matches with this, right? Because here I is on top, so j gets the one on top, and here I is on the bottom, so j gets the one on the bottom. So by just looking at it, you don't have, if I wrote them as j and j prime, which at some point I'm forced to for some other object, you look at this and it's like, wait, is this old in terms of new or new in terms of old? So without indices, there's no clue in notation itself which one is j and which one is j prime, if I wrote it without the indices. But when you look at this, it's like, oh, I know that it expresses the new ones. If you forget which one you call new, which one you call old, you can say primed and unprimed. It's like, oh, I know, this represents the unprimed in terms of the prime. And this represents the primed in terms of the unprimed. And this represents the unprimed in terms of prime. It's a beautiful aspect of tensor calculus that the symbol itself immediately reminds you of where it came from. More question? No, that was it? Okay, so now get ready for second order derivatives. Remember the exercise with the third order derivatives, and you begged me no more? And the point of that exercise, maybe you should say so in the exercise, is to make you suffer so that tensor notation offers a welcome reprieve from the suffering of lack thereof. Let's go back to f of mu, meaning mu1, mu2, as a composite function. What is it called? Composite function? Am I using the right term? Composite function? As a composite function of f in terms of a's, and you plug in how a's depend on the mu's. Let's take the first order derivative. df d mu alpha. Well, we're super good at this now. It just rolls off your tongue. df dai dai d mu alpha. Now we're about to take a second derivative. First of all, tell me how I write, what do I write on the bottom to represent the second derivative? So this represents the two first derivatives, df d mu1 and df d mu2. How many second derivatives are there?
4.
4. mu1, mu2, mu1, 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 mu2, mu2, mu1, and mu2, mu2. So 4. So what am I going to differentiate this with respect to?
D mu beta.
D mu beta. You have to pick a new letter. df d mu alpha means nothing. You have to come up with an expression that represents all four second order derivatives. There are 2 degrees of freedom. There are two, is that the right term? There are 2 live indices in this expression. And by plugging in different alpha and beta, we will be able to identify what d2f, d mu1, d mu2, d mu2, d mu1, d mu1, d mu1, and so forth. So it needs a new letter. Now, this expression, at least early on, you're not ready to differentiate. Because if you want to differentiate to get this, you first need to write down the identity. We could burn 5 minutes and I'll have you try writing out this expression. And all of you will fail. And it's a good thing. It's a good thing. So I'll just show you how to do it once. And then you'll have plenty of opportunity for failure. You basically have to make every single mistake you possibly can. I always tell you this, now I'm saying it on camera. Learning tensor calculus is making every single mistake you can make. So the harder you work, the sooner you'll make every single mistake you can possibly make. They all come in differentiation. So let me show you what you need to do in order to find a proper expression for this. You need to write down the identity in the same set of variables. I should have erased this. I should have erased this. This is not ready for differentiation. I'm going to make it ready for differentiation. In order for an expression to be ready for derivatives, you need to write out the exact functional dependence that's taking place. So f is a function of the mu's. Hold on, I'm going to take this back. That means that df d alpha, d mu alpha is still a function of the mu's, right? Because when you start with a function, that's a function of mu1 and mu2. And you take its derivative, let's say with respect to mu1, which you get once again as a function of mu1 and mu2. Do you agree with me? If this was square root of mu1 plus mu2, square root of, yeah, sure. then the derivative with respect to mu1 would be 1 over 2 square root mu1 plus mu2. And the derivative with respect to mu2 would be the same thing. But once again, a function of mu1 and mu2. So that's why I wrote this here. So it's ready to be differentiated once again with respect to mu1 and mu2. When I take this expression, f is a function of a1, a2, and a3. So when I take this derivative, I will once again get an expression of a1, a2, and a3. And I would then plug in how a1, a2, and a3 depend on mu1 and mu2 in order to differentiate it with respect to mu1 and mu2. So you have to remind yourself of this. When I do this, I naturally get a function that's a function of a's. And I have to once again plug in how a's depend on mu1 and mu2. If f was a1 times a2 times a3, then you plug, then df dA1 would be a2, a3. And you once again have to plug in how the a's depend on the mu's. That's the process of the chain rule. And now I have a function of mu, which is what I want, times dAi d mu alpha. Well, these guys, ai, could be mu1 plus mu1 minus mu2. Mu1 squared minus mu2 squared. That could be the function that it is. So when you take a derivative with respect to one of the mu's, you once again get an expression in mu's. So this is already a function in mu's. So now I have an identity where the independent variable on both sides is mu. And here it's a function of mu naturally. And here you have to remind yourself of how the function of mu1 and mu2 is formed. And now it's ready to be differentiated by the chain rule. Well, actually, the product rule, because it's a product of two things. And even though there's a summation implied, differentiation passes right inside the summation. So you can deal with these things just like they're numbers. Well, they are. There's just summation outside of it. And it becomes, who wants to tell me what the derivative of this with respect to mu alpha is? Chain rule. It's the derivative of this with respect to, now you have to say aj, and then daj, d mu alpha. So it becomes, so you will compare this with your homework. Yeah, I'll show you. D2F, DAI, DAJ, DAJ, D mu. Oh, I'm sorry. We're not differentiating with respect to mu beta. So it's d mu beta. And then this term is unchanged because we're using the product rule. DAI, d mu alpha. If I were doing this, I would maybe rewrite this in alphabetical order, right? The order doesn't matter. These are just numbers. That's one of the advantages of tensor notation. Plus, and you will notice that now I'm no longer writing the functional dependence of the operands, because I'm not about to take a second derivative. If I were to take another derivative of this, I would once again write a function of a, plug in how the a's depend on the mu's. But if I'm not about to take another derivative, well, actually it might be. Homework. DAI. And now this just has to be, now I have to take the derivative of this with respect to mu beta. Well, that's just the second derivative. D2 AI d mu alpha d mu beta. There you go, done. And you can see right from here that the third derivative won't be so so difficult. How many identities is this?
4.
4. How many terms does each identity in the sum? How many terms are there total?
12.
Let's calculate. Yes, 12. Yes. 9 in this. So when you were doing it by hand, right, you had 12 terms. Am I right? 2 is better than 12. Everybody's going to agree with me. And the full generality is here. So this is, anybody has a book handy? Oh, right there. This is an equation. If you look at equation, hold on. There we go. Second derivative. Oh, exercise 34. This is exercise 34. Invites you to evaluate these derivatives without the benefit of the tensor notation. So whatever answer you got in exercise 34, this should translate to it. So if we look at one of these, d mu1, so back there they were called mu and nu. So d mu, we just have to take one here and one here, because these are live indices. And then the 12 terms that you obtained, so you should compare the expression that we just got, plug in different values, and compare to what you got in exercise 34. And this expression should represent what you had in exercise 34. Now I will take advantage of the 10 minutes that I have remaining. Yes.
I see the 4 identities. Where are the 12?
Terms? Well, there's the summation over i's and j's.
That's 9.
That's 9. Plus here, there's summation over I. That's 3.
So a
Total
dummy
12.
index does not have to
No,
be...
this, technically speaking, you might want to use a different one here. But this I doesn't mix with this I. This
So
one is,
J is not a dummy index in the second term, but only in the first.
there's no j here.
Right, so you don't look at the whole
That's-
thing as
You don't
well.
look as a whole thing with it. Yeah, this has its own maybe double summation, and this has a single summation implied, and they're different. Yes, they don't mix that way. Okay. I will brave this. This will be your homework, but I will just get you started. So let's look at this identity. That's the Jacobian identity. That reads J I prime. This is not the one we derived, this is the equivalent one. J equals delta I J. And we don't need to spread them like this. Not even here. Because we just know that the first one, upper one is first, and lower one is second. So this is an identity that was obtained by differentiation. We can go to second order. We can take the derivative of it one more time. Let's introduce these objects. So J I prime was by definition d z I prime. And to be a little bit more careful, I will put the functional dependence here. It's the function of how old variables depend on the new variables. But you could take another derivative of this, the second derivative, dzj prime. And that would be denoted by I prime, j prime. It's this second derivative. And by looking at the indicial signature of this one, let me make it a little bit more clear, font-wise. I prime, j prime. You actually can remind yourself immediately what it came from, where it came from. This is the unprimed variables as functions of the prime variables, that relationship differentiated twice. Of course, there's some kind of relationship between the second order. This is the relationship between the first order derivatives. There is some kind of relationships between second order derivatives. And of course, they're obtained by differentiating this expression one more time with respect to something. But before you can do it, but of course, before you can do it, you have to once again write down an identity in terms of the independent variables. And I'm going to write down this identity and stop there, and you'll figure it out as part of your homework. So when I look at this expression, I first have to decide whether I will make it all an identity in terms of the prime variables or the unprimed variables. Here I actually have a choice. We'll go for the unprimed variables. So this guy right here is already naturally expressed in terms of the unprimed variables, because this was the derivatives of r's and thetas in terms of x's and y's. So this is already a function of the unprimed variables. So I can just write that this is j I prime j as a function of z's. And don't worry about my saving you right now from making a few mistakes, because there is plenty more for everybody to make. There's just no way to figure all this out without me correcting the mistakes, or you correcting your own mistakes. But this, how much did we make?
That was just like 10 seconds.
So, this one being the derivatives of r and theta in terms of x's and y's is already a function of x's and y's unprimed coordinates, so there you go. This one came from differentiating the functions of x's and y's as a functions of r's and thetas. So it naturally appears as a function of r's and thetas, in other words, of the prime coordinates, and you have to plug in how the prime coordinates depend on the unprimed coordinates. Now you have an expression that you can differentiate with respect to zk, because everything is a function of zk. Now for the right-hand side, it's just the delta function. It came from differentiating x's and y's in terms of x's and y's, so it's already, even though it's trivial, lines and zeros, but you can think of it as a function, constant functions of x's and y's. So when you differentiate the whole thing with respect to zk, the right-hand side will turn into 0, because these are constant functions. But something much more complicated, very much non-trivial, will happen on the left-hand side. This will turn into zj I prime jk very easily, but this one, you will have to apply the chain rule. So very short expressions, but very intense. And the next lecture, we're going to talk about the tensor property. The tensor calculus will start, the gradient will be fixed, upper and lower indices will be explained, and the whole point of tensor calculus will be revealed in the next lecture. So see you next Friday. Yes?